So we were discussing yesterday the resist contrast curves, right? And prior to that we had a discussion of the modulation transfer function. So the modulation transfer function essentially is about the optical system and then your mask and the image that is actually incident or is appearing on the image plane. Okay, but then the image has to be transferred to the photoresist. Yeah, so then the characteristics of the photoresist is very important. So this is the resist contrast curve is actually one way to capture it, and we have seen this. And depending on whether it is optical lithography or electron beam lithography, you can actually you are looking at the total energy incident on the resist, okay, absorbed by the resist locally. So this is natural because the photochemical reactions that are happening would require some energy, so you are looking at the energy, right? And in the case of electrons, it's easy to measure. That is actually the current. The voltage is a constant, acceleration voltage is a constant. So one of the easy to measure parameter here is actually the current. So you measure the beam current and then integrate it over the period of time. Yeah. So you have the dose is defined in this case in terms of microcoulombs or coulombs per unit area. So in the other case, we were when you talk about the light intensity, you're usually talking about what is the power per incident per unit area, so watt per centimeter square, and then you are interested in the energy that is actually accumulated or incident over a period of time. Okay, so integrate the light intensity as a function of time. Usually it is, these are constants, right? You are not going to change the light intensity as a function of time. So you just take the intensity of light in watt per unit area and multiply it with the time, so you get the energy per unit area. Okay, so dose can be, in the case of photolithography, this would be in joules per centimeter square. Usually the energy is small, so it's millijoules per centimeter square or so. And then in the case of electron beam lithography, you look at the coulomb per centimeter square unit area. Now if we combine this, the resist properties and then the modulation transfer function, we should be able to actually understand on what would be the shape of the photoresist that we would get after exposure and development. Okay, so let us say this is the modulation transfer function, right? You have the intensity of light actually that is going up, and then this is the image that is formed, right? And then the peak value is, so this is a relative, okay, and then that is normalized to the peak value, okay, and then it doesn't go to zero because of interference effects from two neighboring features. There is some residual dose. So you have the modulation transfer function. We actually defined it in terms of what? Modulation transfer function was something, that you had the I max minus I min divided by I max plus I min, right? Here you are essentially plotting on this axis not the modulation transfer function, actual dose. So you take the intensity of light that is falling on it, watt per meter square, multiplied with the time. So let us say you exposed it for 10 seconds. Okay, yeah, I'm just giving you some number, and then so you take this watt per meter square multiplied with 10 and you get the energy that is incident. Okay, so that is what is being shown on the vertical axis here. Okay, and it is relative, so you are taking the maximum of the energy and divide it by the whole thing by that number, so you get the maximum value to be 1. Got this point? Is this clear? Okay. So what we need to do now is we look at two parameters from the resist contrast curve, that's Q0 and QF. Okay. Assume it to be a positive resist. Okay. So can you now tell me what would be, this is the position, yeah, this is position on the wafer. Okay, this would correspond to some features. So positive photoresist means wherever you expose it to light and you dip the whole thing in a developer, the resist will be removed. Okay. Now can you draw the profile, how the resist would look after development? Okay. So those who have the slides, you already have the solution, but just try to find out. Meaning you can, how did you get that thing in the resist? Or if you don't have it, it's a good thing. Also, you can just try it out. Or maybe those who have the slide, just close the slide and just try to work it out yourself. So let us take this. So what would be the resist remaining in this range? Huh? All of it will remain, yeah, because you need a minimum dose of Q0 to be incident in that region for the resist to undergo sufficient photochemical reaction that you allow the developer to etch it. So here it would be flat, so whatever was there, whatever resist you deposited, that would remain, right? And now what about this part? So now the exposure dose, relative exposure dose is increasing, okay? Then what happens? So you can see that what happens when the dose is more than QF? Completely removed. Okay. So you can see that for this range, the remaining resist thickness will be 0. Okay. So you got at least two regions. So I can then extend this. So in this region, it would be full resist would be remaining. Here 0, okay, and here again full resist, and here 0, okay. So that much I can say. What about the regions in between? So between this and this? Yeah, so it will be partial. So you can actually then draw the profile of this resist, right? Okay. It will not drop vertically, but there will be a slope. Okay, and same thing here. So students who would actually go and make devices in the lab, this is a very important consideration. Okay. Now we would really like to so this is what you get. Okay, some schematic representation. I'm not saying that here this question, what is the resist contrast curve, we don't know. So we are assuming some monotonous characteristics is very well defined linear kind of thing, right? But we are so this is kind of a representative thing, not necessarily exact shape. So you can have sometimes something like this, and so on and so on. So we would not worry about the exact functional form. Okay, now what is the implication of this in for things that you want to mask? Okay, so the photoresist is supposed to actually operate as a mask. Okay. Now, one application we have discussed often is what is called lift-off process. Lift-off process. You remember what is lift-off? What is lift-off? So we had done, in the previous quiz, there was this question that if you have a thin film deposition using ALD, and then what was the other thing? Sputtering and MBE. Yeah, what would be the profile and the resistance essentially coming from the thickness of the deposited layer on different facets of the surface. So let's say I want to do a lift-off process. So the lift-off had worked this way, that you have the photoresist and you have developed it. Okay, and then you're going to deposit metal on top. Okay, and the condition was you are not going to etch the metal, by the way. Now this is for situations where etching the metal is not practical. Okay, so for example, gold, it's very difficult to etch, and you need aqua regia, and then aqua regia may attack other things on the wafer. Okay, so many a time people actually try to do lift off of gold. Yeah, so you deposit gold, and let's say I use a very high vacuum technique where it is actually line of sight deposition. So on vertical walls you have no deposition. Okay, so this is what we discussed, right? Suppose now I use this resist, can I do a good lift off? So what is the next step in the lift off? So I deposit gold and it gets deposited on the flat surfaces, right? Here, 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 and so on. Okay, and on the vertical walls I don't expect any deposition, right? And then I would actually etch the photoresist. Okay, so whatever gold is on top of photoresist will be removed along with the photoresist. So that is what you are lifting it off. Okay, so that is the name. Now if I want to do a lift off, can I use this photoresist and this process that we are discussing? Will it actually give me a good lift off process? Good lift off. Why not? Edges are not vertical, right? So even in a line of sight deposition, I would get some film deposition on the side walls. Here it would be worse. Okay, so this is a very important consideration, and most of the time the lift off process is seen to be very difficult thing to reproduce for most of our students, and one reason that I have found is that nobody does any analysis of the profile of the resist after you actually develop it. Okay, so when you do this lithography things, one of the very important thing you need to worry about is actually the profile of the resist. Okay, and if the features are really small, there is no other way than doing a cross-sectional SEM of these features to see how this works. Yeah, so scanning electron microscopy has to be done, and then again very important, in scanning electron microscopy you are going to use electron beams. Okay, so it is very difficult to do any imaging if your material you want to observe is dielectric using an electron beam, because you are actually, what are you looking at in scanning electron microscopy? That is one name, but it is also called secondary electron microscopy. Yeah? So you actually have this electrons going and hitting the substrate, and they will emit, meaning a lot of things happen there. Okay, so one of them is actually the material will emit secondary electrons, so you are actually observing them. Yeah, But suppose this material is charged, so you are actually bombarded with a lot of electrons, it becomes negatively charged. So then what happens? The incoming electrons will now be deflected. Okay, so I don't get secondary electrons. Of course, there is another technique called backscattered electron, meaning the same system but a different type of detector is used for this. So, but the secondary electron microscopy is the most frequent thing, and because backscattered does not give you good resolution, okay, but it is good for certain other things. Backscattering depends on the elemental mass, okay, so it gives a good contrast if you have materials of different elemental mass. For example, I can easily contrast between silicon and gold and so on and so forth in a backscattered image. Okay, so this is a very important consideration. So liftoff is something that we have already seen. Okay, but now suppose I want to use this resist for ion implantation. Yeah, ion implantation. Okay, let's just come back to this liftoff process. What would be an ideal resist profile? Ideal resist profile, if I want to guarantee liftoff. Can you just try this? Okay, so he's saying that okay, Q0 and QF is, you have very sharp resist contrast. Okay, so that is one thing. Okay, so a very sharp resist contrast curve. So this slope is here very sharp. Okay, so that is one thing. But even if that is not the case, meaning I would really like to have a profile. I am not talking about the process. So process we can discuss later on. But if I really want to have a process, okay, and want a resist profile, I am asking you what would be a good resist profile, okay, which will guarantee a liftoff. Vertical walls is okay, but then you are counting on the modulation transfunction of the, so that depends on the features on the mask, yeah, how close they are and all this. So one thing is, so you have this is the profile that we are discussing, right? Suppose I have something like this. Okay, so instead of this, so this is called a re-entrant resist profile, okay. So this is vertical, but this is the re-entrant resist profile is actually a little bit inside. Okay, so what this may look a little bit fanciful, but then people do all kind of tricks to get here. One of them is actually deposit two different photoresists. Okay, two different photoresists. They have different resist contrast curves, for example. Okay, so that when you develop, the bottom part is etched more than the top part. So you have something that goes under this. Okay, but for your line of sight deposition, this edge is the mask, right? If I have something like this, right, and I do the deposition, where will it get deposited? Here, right? So this is the re-entrant profile we are talking about, and the material will get deposited like this, because this is the okay, will not get deposited under this cave, for example. Okay. Now there are other issues. So suppose I use this photoresist profile for masking something. Okay. So I'm drawing on the two sides of the same photoresist profile, yeah, two shapes. Okay. So this is something that we will discuss again maybe when we do discuss about ion implantation. So ion implantation, I am implanting ions, right? And this is photoresist, right? So the ions would have certain energy, okay? They get implanted, okay? But in this region, they would get implanted into the photoresist, not into this, okay? But then this part, for example, the ions have certain energy, so that the doping concentration or the implanted ion concentration comes to nearly zero or negligible within this depth. Okay. And I have a similar thing here. Okay. So this is what I would really like to have, right? But what happens here? These regions. Okay. So some of these dopants would actually go in. Yeah. So instead of this profile, I may get something that is extended. Okay. But even with a very sharp resist, I would get a little bit of thing in here because of scattering of these ions within the material. But if I have a resist profile like this, then I may have a bigger junction is actually spreading onto the sides. Okay. So this is a very important consideration. So this essentially tell you a typical resist process, but you know the photoresists are usually highly guarded secrets. All this chemical composition and the mixtures they use are highly proprietary. So usually the companies that sell this photoresists don't tell you what are the things in there, in what proportion they have mixed it, and so on and so forth. Okay. But they would actually always come with a, sometimes they give you the resist contrast curves, right? What is the recommended process, okay, you should do. So this is just one of the examples. Always you should look at the details of the photoresist data sheet to see what exactly is recommended by the manufacturer, and you start with that process and then you can play around that baseline numbers. Okay, so this is a generic thing, so you may or may not do all this in your actual process, right? So you have a wafer surface, so that can be silicon, silicon dioxide, silicon nitride, or mixture of these things, right, at different places, and you need to clean the surface, and so usually you use some aqueous solutions for cleaning, okay. So you need to remove the water from this, so there is a dehydration, bake, essentially you heat it to some close to 100 degrees centigrade or something. And then very important thing is that the photoresist, okay, when it is deposited, should stick to the wafer surface. Yeah, because I am going to do maybe a lift off process, or actually even otherwise photoresist I deposit, right, I need to do an exposure, and then I am going to develop it. So when I develop it, I am going to take this wafer and put into some solution, yeah, some liquid, okay. So if the photoresist do not stick, it will just be removed from the wafer surface. So it should actually have good adhesion to the substrate, And sometimes people do this thing. So this is liquid hexamethyl disilane, and this is chemical composition. So this can be spin coated, or you create vapors of this in an oven, okay, and you keep your wafer in there for a couple of minutes, and this thing gets deposited on the wafer surface, okay, and then you get better adhesion of the photoresist. So this is a very commonly employed process. Then you do a resist application, photoresist. So this is by spin coating process. So usually the wafer is placed on a circular disc, okay, which can be rotated at high speed, okay, and then in the middle of this wafer you are actually dropping, okay, measured quantities of the photoresist, okay, and then there is some this is a typical, these are typical numbers, but there is usually a spin schedule, which means that you don't go from 0 to 6000 rpm, but you will actually start a little bit slowly, maybe 1000 rpm for a certain time, and then higher, and then you get to the full speed and then reduce it. So there is a spin schedule, but this is the typical spin speeds that are used, and you can see that it's a fluid, right? So the thickness, uniformity and so on would depend on what is the spin speed and the spin schedule that you use. Okay, if you use really very fast spinning, you may get very thin resist. In fact, the photoresist will also splash around. So you actually do this process in a closed chamber. Okay, and the photoresist is sticky stuff. So you know after some time the solvents will evaporate and so on and so forth. Very important thing for photoresist is that this is a photosensitive material. Okay, so you can see the bottles of photoresist. They are actually glass bottles. Okay, nearly opaque. Yeah, glass bottles. Okay, so you don't want any light to get in. They're sensitive to moisture. Okay, so the thing is now photoresists usually come with a shelf life, typically in the range of 6 months to 1 year. Okay, so now we have a big challenge because photoresists are also inflammable stuff. Okay, so they may not allow you to bring it by flight. Yeah, so and a bottle of photoresist which is maybe 2 liters have to come from United States to India, for example, or Singapore. Okay, Singapore is closer, or from Japan or somewhere. Okay, and you know it's inflammable, so it cannot come in all ships. I'm just telling you some difficulties. Yeah, it cannot come in all ships, for example. Okay, and but it has a shelf life of 6 months. Okay, so you can see this. You know this whole discussion about when you go to high tech, where very special materials are required and so on. You can see this. You know, people think, okay, India can be a low cost manufacturing place. Yeah, but it's not true actually. That is, you know, meaning low cost manufacturing in what sense? Because people are cheap. I'm sorry. Maybe you don't have to pay a lot of money to somebody to work, right? You see, actually Donald Trump is saying that this car part that is imported from Mexico, this should be made by people who actually have been paid at least $15, $16 per hour. Okay, $16 per hour. So you can calculate what is that? 70 rupees dollar, 700, 1,500 rupees per hour. Okay. Now, if that person works for 1 day, 8 hours, calculate how much it is, right? Meaning 1,000 rupees and 8,000 rupees roughly. Now you can see a lot of these people are sweeping The roads here gets 8,000 rupees per month. Okay, so this is the thing that we are talking about, right? But then if you look at, this is, manpower is a very important component of the whole manufacturing cost. But in recent times, there is something the economists call as productivity. Okay, how much work a person can do. Okay, but it's not just the person plus machine. Yeah, so I'm actually there, actually doing something, right? Moving some earth from somewhere, but it may take me 100 days to move, yeah, some earth, but then I come with a big machine, right, and do the whole work in 1 hour. So and the machine is much more productive than I am. Okay, so you can see this whole manufacturing has moved into a thing where you don't, or the human resource needed is less and less. Okay, so you're talking about driverless cars. What will all these guys do? Meaning taxi walas. Okay, so of course the productivity is going to increase, but then the human resource you need to actually run these things also decrease. So increasingly in manufacturing, this argument of cheap labor is not anymore important. Okay, only thing is where you need people, so where you need the high level human resource, right? That is where, meaning we may still have an advantage, but I think how high is our people's overall, right? The education level and so on become very, very important. Okay, so this is something that we should keep in mind when you talk about all this manufacturing and so on. Right? So, okay, so now coming back to this spin, in what context did I start talking about this? Pardon? Yeah, you are, okay, so we talked about this, right? So you get this ring from United States or Europe or somewhere, and already 3 months is gone. Okay, already 3 months gone. Now you can keep it for 3 months. Okay, but on this guy who is actually there in Germany, right? He orders, next day it comes to his office. He can keep it for 6 months. Okay, see the difference, right? So obviously then we are in effect paying double for the same thing than a German person. Okay, now if I add this cost of the photoresist and the person who is working, okay, I actually have to pay this much compared to a German person, right? Meaning in Germany, let's say instead of 3 months, you can keep it for 6 months because I have spent already 3 months of the lifetime in the sea. Okay, so if this person, meaning we are getting so much paid and the German guy is getting so much paid, but still the total cost is the same. You get the point? Yeah, so this is something we need to keep in mind. For example, we are doing some exercise to find out whether we can, do silicon manufacturing in the country, high purity silicon for solar cells, because we are going to install a lot of solar farms. Okay, now the whole calculation came out like this, that of course the labor cost here in India for manufacturing is low, but we are actually paying a lot more for electricity. Industrial electricity tariffs are quite high in India. Okay, so even if you reduce, unless you reduce this electricity cost, you can't compete with China or even some other Eastern European countries or some of the Asian countries. Okay, so this talk about the inexpensive labor in the country is not necessarily very attractive if you look at the overall picture. Okay, so now you have the pre-bake of the resist. So this is spin coated, and then you're going to actually bake it. What are you trying to do in the baking? So the solvents in the photoresist should be removed. Okay, so it's a fluid, right? Yeah. So I have to actually make it a solid. So I am going to remove all the solvents in this. So this would be done for, these are some typical temperatures, and then the idea is to remove the organic solvents in the resist, and then you will do the exposure. Okay, so align the wafer and expose the resist, and there is something called post exposure bake. Okay, so after the exposure you get some features in the photoresist, right? So some regions are exposed to light, right? And you have seen this Q0, QF and so on. So they got different amount of light. And there can be some roughnesses in the features because of standing waves, for example. Yeah, we will see that in a moment. So you have the light that is coming in, okay? And if part of the light actually gets reflected, then you can create standing waves in the photoresist. Okay, so in that case you would really like to, you may get some strange features which I'll show you on the next slide. So if you do a post exposure, this is seen to actually be reduced, the roughness. Okay, so it depends on the photoresist. This is one typical number. Yeah. So you have done this post exposure bake. Still the photoresist is there everywhere on the wafer. So you need to do what is called the resist development. So this is done in a recommended developer. So the company that produces the photoresist usually also give you the developer, okay, which will work with that photoresist, and then you essentially dip it, the whole wafer, in the developer. And you can do a post develop bake, essentially to remove the solvents from the developer that is still remaining on the wafer. Okay, so this is the process. So kind of low temperature baking is done many times. Yeah, so 140 degrees centigrade is also temperature at which you bake your bread. Okay, if you bake bread, for example. Mask. So now you can use this photoresist as a mask, and mask can be for wet etching, dry etching, and implantation. So these are the typical processes, or for lift off, for example. And after that you remove the photoresist. Okay, so this is now these are some typical things used for removing the photoresist. So you have isopropyl alcohol can be used, acetone can be used, or there are also resist removers again provided by the photoresist manufacturers, so that can be used. But in some cases what happens, so dry etching using oxygen plasma, because the resist these days are organic materials, so you can burn the photoresist, okay, using oxygen plasma. Now the other thing that is used, so if you can't remove the photoresist by these techniques, then you go for piranha solution. Yeah? This is the sulfuric acid hydrogen peroxide mixture, and this is quite aggressive. Okay, so why you need to resort to different kinds of things? So it may not be that you know isopropyl alcohol can be used for removing any photoresist. That is not possible, and the reason is that after your photolithography, okay, you're going to use the photoresist as a mask. Yeah, so whatever you're doing here, right, may result in some changes in the properties of this material. Okay, so for example, if I use dry etching, so dry etching essentially is done in a plasma. Yeah, so in a plasma, the photoresist may become denser, or might have gone through some chemical reactions with the free radicals and other things in the plasma. Okay. Ion implantation, again, you are actually bombarding the surface with high energy ions, so that may lead to some polymerization reactions and some stuff that would then, or maybe the elements that you use for creating these ions react with the photoresist, and then you get some products which are difficult to remove using the organic removers. Okay. So then you may have to resort to this kind of very aggressive wet chemical processes, and this is another one. Okay. Ammonium hydroxide, hydrogen peroxide mixture. So these are quite aggressive chemicals. But then of course one very important thing that students don't do many a time is to inspect these wafers to make sure that the photoresist has been removed. Okay, very, very important process. And this again, a lot of these inspections can be done using very simple microscopes. Yeah. So if you go to the CN lab, we have a microscope that can give you a resolution of 1 micron. Features can be actually seen. 1 micron. Yeah. So for most of the applications, that is good enough. Yeah. You do a good microscopy, it takes you 5 minutes, and that actually tells you whether you should proceed further with this wafer. Okay. Okay, so now the one concern is that this is an image from this book by Plummer. So what you are trying to do is you have a silicon wafer with certain features on the surface. Okay. Now you have photoresist and you are trying to expose this, right? This is your mask, and there is some photoresist, and the light is going through this photoresist. Okay, and this is your transistor, and you deposited something. So in this particular case, it can be some oxide, silicon oxide, okay, with certain properties, and then you are exposing this. So light comes through, and then you see these features here, right? Yeah, and the refractive index of these materials could be different, right? Because you are using silicon nitride, for example. This would be a spacer, silicon nitride. This can be maybe a metal, I don't know. So there can be reflections from the surface. So because this is your photoresist, right? And it would have some absorption coefficient. But typically the photoresists are thin, maybe a few hundreds of nanometers. Yeah, meaning thick photoresist can be maybe a micron, 2 micron something, but it's not, maybe not necessary to absorb all the light. Yeah, because it has a finite absorption coefficient, right? So the light that goes through will get reflected. Okay. So what would be the consequence of it? If it is specular reflection, what happens? So the same light is going through the photoresist twice, more likely to be absorbed, right? So apparent dose will increase with specular reflection, but what about this? Diffused reflection, non-specular reflection. This part is not supposed to get any light in the first place. Okay? But then you will get near these edges, part of this can be exposed by the reflected light. Okay? So that is the first problem. So this means that the feature that you want to etch is only this, but it might get broader because of reflections. Okay? So one of the things that is being done here in this case is to what you call as the anti-reflective coatings. Okay? You deposit an anti-reflective coating on the wafer surface so that you reduce the reflections. Okay. Now the other problem is also you may get what are called standing waves. So standing waves could actually lead to features of this kind on the photoresist. So you can see this here. If you look at this edge, it's wavy. Okay, so the edge of the photoresist is wavy, not straight.